What would happen if the universe you're living in is not the final version of reality? For more than a decade, physicists have quietly carried a hypothesis that sounds almost like a secret of the cosmos, that everything we see, every star, every atom, every breath may exist in a temporary state of the universe, a false vacuum delicately balanced between what is and what could be. Not unstable in a frightening way, but in a way that makes our existence rare, precise, and extraordinary. Imagine the entire universe as a candle burning its flame steady and calm, yet not having reached its deepest stillness. If this is true, then our universe is not a completed story, but only a beautiful chapter in a much larger book of reality. So right after this, let's explore what state the universe is currently in, and how we can ensure that life will continue. For most of human history, reality has seemed firm beneath our feet. The sun rises, matter holds its shape, and the laws of nature behave with such consistency that we rarely doubt them. Gravity, light, time, the particles that form everything, these feel like unshakable foundations. But in the late 20th century, physicist Sidney Coleman proposed a possibility that gently unsettles that certainty. He suggested that the universe may not be in what physicists call the true vacuum, the lowest, most stable energy state of the quantum fields that define reality. Instead, everything around us could be suspended in a false vacuum, a state that appears stable, behaves stable, and can endure for billions of years, yet is not the deepest resting place available. To grasp this idea, imagine a marble in a shallow hollow on a hill. It sits still undisturbed. It may remain there for a very long time, but a deeper valley lies below. A small nudge, a subtle shift, and the marble could roll into a more stable resting place it had never reached before. Reality, Coleman suggested, might be like that marble. The thought is not meant to alarm. Rather, it opens a different kind of curiosity, quiet, reflective, and steady. If the universe is not truly finished settling, then the fact that it has held together long enough for galaxies, stars, life, and consciousness to emerge becomes even more remarkable. To understand why scientists take this hypothesis seriously, we need to look beneath the familiar world of objects and into the modern foundation of physics, the world of quantum fields. It may sound abstract, yet the idea is both simple and elegant. In current physics, particles are not viewed as tiny solid grains. Instead, they are vibrations, ripples in invisible fields that fill all of space. There is a field for electrons, for quarks, for photons, and for every fundamental component of nature. What we call a particle is simply a localized disturbance in its corresponding field, much like a small wave on the surface of a vast ocean. Even what we casually call empty space is not truly empty. Every quantum field has a baseline vibration called zero-point energy, a subtle, unavoidable trembling that remains even in perfect cold and perfect darkness. Space is never still. It holds a quiet energy that never fades to zero. And this is important because in physics, a vacuum is not the absence of everything. It is the lowest energy state a field can occupy. The question is, are the fields of our universe truly at that lowest energy state? After the Big Bang, the universe was a storm of energy, hot, dense, chaotic. Quantum fields were highly excited, fluctuating with extraordinary intensity. As the cosmos expanded and cooled, these fields settled like molten metal cooling into form. Most appear to have reached their stable resting point. But what if one of them, especially one that shapes the structure of matter, did not settle completely? What if it stopped just slightly above the deeper state, like a ball that came to rest before reaching the bottom of a valley? This is where Coleman's hypothesis enters. The universe might be living in a state that is stable enough but not ultimately final. Physicists visualize this through an energy landscape, a map of possible energy states for a field. A true vacuum is the deepest valley in this landscape. A false vacuum is a higher valley, stable, long-lived, but not absolute. A field could become trapped there if the universe cooled too quickly, never having the chance to slip into the lower valley. If reality sits in such a false vacuum, it could in principle transition to the true vacuum through a process called quantum tunneling. Unlike a classical ball that must roll over a hill, quantum mechanics allows a field to appear on the other side of an energy barrier without climbing it. If that happened, a new bubble of true vacuum would form, initially microscopic, then expanding at nearly the speed of light, rewriting the laws of physics as it spreads. There would be no signal, no warning. The transition would be instantaneous for anything it touched. And here the mind might naturally pause. Because for all the elegance of this idea, the universe has existed for 13.8 billion years without such a transition. Stars have burned, galaxies have matured, and life has had time to arise and wonder. If we are in a false vacuum, it is not a fragile one, it is astonishingly enduring. Reflecting on this does not make existence feel unstable. Strangely, it does the opposite. It highlights how extraordinary it is that the universe, even if not at its most stable, has remained balanced for so long. Stability, even temporary, has been generous enough for complexity, meaning, and awareness to unfold. When viewed this way, the hypothesis becomes less a threat and more a perspective shift. It invites us to see reality as dynamic rather than fixed, as part of a process rather than a finished structure. The universe may not be a monument carved in stone. It may be a moment suspended in a much larger transformation. And if that is true, then our existence gains a quiet significance. We are living inside a rare chapter of cosmic history, a stable pause long enough to allow thought and curiosity to take shape. The idea of a false vacuum doesn't diminish the beauty of the universe, it enhances it. Because if everything is temporary, then everything is precious. The stars shining tonight are part of a delicate balance that has held long enough for us to witness them. This chapter is not about conclusions, it is about opening a door gently to a deeper view of reality. A view that begins with a simple, almost whispered question: is the universe resting, or merely resting for now? In the next chapter, we will look more closely at what this vacuum truly is, how physicists came to understand the quantum fields that form the fabric of existence, and why this question about stability is not speculation alone, but rooted in the structure of modern science. To understand whether the universe could be resting in a temporary state, physicists first had to understand what the universe is made of at its most fundamental level. That journey surprisingly began not with cosmic questions, but with a simple desire to return to pure science after a chapter of human history defined by destruction. In 1947, a quiet gathering took place at Shelter Island, a small retreat off the coast of New York. Only 27 physicists attended, yet the meeting would redirect the course of modern physics. It was the first major conference after the Manhattan Project, an effort that had demonstrated the terrifying power locked inside matter. At Shelter Island, the mood was different. Physicists wanted to understand nature again, not weaponize it. They were searching for a language capable of describing the underlying rules of the universe with clarity and elegance. Among the ideas discussed there, two young physicists would go on to reshape the foundations of theoretical physics, Richard Feynman and Julian Schwinger. Their work, approached in very different styles, led to what we now call quantum field theory, a framework that describes particles not as small objects, but as excitations of fields that fill all of space. Their perspectives were distinct yet converged on the same truth. Reality behaves like a set of vibrating fields interacting with one another. From this framework grew the standard model of particle physics, a remarkably concise description of the building blocks of the universe and the forces acting between them. It is not a model of planets or galaxies, but of the ingredients beneath all structure, the elements that every atom, every star, every living being is composed of. At its core, the standard model divides the fundamental components of nature into two categories: matter and forces. Matter is built from particles known as fermions. These include quarks, which link together to form protons and neutrons, and leptons, a family that includes the electron. 6 types of quarks and 6 types of leptons make up everything that has mass and occupies space. 12 fundamental building blocks, no more, no less. But matter alone cannot form a functioning universe. It needs ways to interact, to attract and repel, to bind and transform. This is the role of bosons, the carriers of forces. Photons mediate the electromagnetic force, allowing atoms to hold together and light to shine. Gluons carry the strong force binding quarks into protons and neutrons with immense strength. And the W and Z bosons carry the weak force responsible for processes like radioactive decay and the fusion reactions that once powered the early universe. Together, these particles allow matter to behave, evolve, and structure itself. Yet even this particle-based description is not the deepest layer. Physicists now understand that fields come first, particles come second. A particle is not a tiny solid. It is a ripple in a field, an excitation that we momentarily detect before it fades. There is an electron field, a quark field, a photon field, and so on, each extending throughout all of space. Space, therefore, is not empty. It is a medium filled with overlapping fields, each capable of vibrating, interacting, and carrying energy. Even in complete darkness and perfect stillness, these fields cannot be entirely quiet. Quantum mechanics tells us they possess zero-point energy, a faint irreducible trembling built into the fabric of reality. Stillness at the smallest scale is an illusion. This shift from particles to fields paved the way for a new understanding of nature. But it also required a new kind of mathematical discipline, one rooted in the concept of symmetry. Here a profound insight emerged from the work of mathematician Emmy Noether. Her theorem, considered one of the most beautiful results in theoretical physics, revealed that every symmetry in nature corresponds to a conservation law. If the laws of physics do not change with time, then energy is conserved. If they do not change from place to place, then momentum is conserved. Symmetry was not simply an aesthetic property of equations, it was a fundamental principle of reality. This idea became essential when physicists sought to unify different forces under a single framework. They developed what is known as gauge symmetry, a type of symmetry that applies not to shapes or rotations, but to the internal settings of fields themselves. In simple terms, it states that certain transformations of a field should not change the laws of physics. This principle successfully explained the electromagnetic force through a symmetry called U1. Encouraged by this success, physicists attempted something more ambitious to unify the electromagnetic force with the weak nuclear force. The weak force behaved very differently, short-ranged rare and mediated by heavy bosons, but mathematically the two forces seemed to share a deep structural similarity. If a broader symmetry could describe them both, nature would appear more elegant, more unified. This led to the development of the electroweak theory, built on a combined symmetry called SU2XU1. It was a brilliant idea, two separate forces described as two faces of the same deeper interaction. However, there was a problem, one that threatened the entire structure. If the electroweak symmetry were perfect, then the W and Z bosons should have no mass at all. They should behave like photons traveling long distances and spreading influence across the universe. But experiments clearly showed the opposite. The W and Z bosons are heavy, so heavy that the weak force they carry fades almost instantly at short distances. And if electrons were also massless, atoms could not exist in stable form. Something subtle had happened in the early universe. The symmetry had not vanished, it had been broken. The equations remained elegant, yet the universe itself had taken on a different configuration, one in which certain particles gained mass. This is where the path begins to turn toward the mystery that Chapter 1 introduced. For if the standard model uses symmetry to describe forces, and if mass appears only when symmetry breaks, then the key to understanding whether the universe is in a temporary state lies in the mechanism that broke that symmetry. The standard model, as successful as it is, leaves us with a quiet question. What caused the symmetry to break in just the right way to shape the universe we see? And is that broken state the state that gives particles mass the deepest one available? Or only a step along the way? These questions lead directly to the concept of the Higgs field, a field unlike the others we have discussed. It does not carry a force in the traditional sense, nor does it form matter. Instead, it sets the stage on which mass becomes possible. The Higgs field created a shift in the structure of the universe itself. But before exploring how the Higgs field changed everything, it helps to appreciate the remarkable position we now stand in. The standard model provides a framework of almost astonishing accuracy. It has predicted particles before they were discovered. It has described interactions at scales far beyond direct perception. And yet within its success lies a subtle clue: the mechanism that grants mass and stabilizes the structure of matter may not be as immutable as it seems. If Chapter 1 posed the possibility that the universe rests in a temporary state, Chapter 2 reveals the structure of what is resting, a tapestry of fields, symmetries and interactions woven into a delicate balance. The next step is to understand how symmetry was broken and how a single field, the Higgs field, tilted the landscape of reality in a way that allowed particles to settle into form. For within that tilt may lie the reason the universe appears stable, and the reason it might not be. If the standard model is the architectural map of the universe, then symmetry is the quiet principle that guided its design. To understand how the universe once held a more unified form, and why it later changed, we must step into a chapter of physics where simplicity and elegance shaped everything. Symmetry in everyday life is easy to notice. A snowflake, a calm reflection in water, a perfectly balanced pattern all bring a sense of harmony. In physics, symmetry carries a similar beauty but with deeper consequence. It is not merely visual or aesthetic. It determines how the laws of nature remain consistent across space and time. The universe in its earliest moments appears to have been more symmetric than the universe we see today. Forces that now seem distinct were once intertwined. Particles that now differ in mass may once have been indistinguishable. To appreciate this, we need to look at how physicists came to understand the forces of nature as they exist now, and how they might once have been one. Today, 4 fundamental forces govern the universe: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Each shapes the behavior of matter in its own way. But in the realm of particle physics, attention turned to 2 of them, in particular the electromagnetic force and the weak force. They seem to share a mysterious connection. The electromagnetic force is familiar in everyday life. It shapes atoms, allows chemistry to exist, and carries light across the cosmos. The weak force is less visible, acting over incredibly short distances inside atomic nuclei. Yet mathematically, physicists noticed echoes of one within the other, a suggestion that the 2 might not always have been separate. The principle that binds them is something called gauge symmetry. In simple terms, gauge symmetry means that certain transformations, changes in the internal settings of a field, should not alter the laws of physics. This principle had already succeeded brilliantly for electromagnetism through a symmetry called U1. It suggested that the force we know as light emerges naturally from the demand that a symmetry be preserved. Could the weak force also arise from a symmetry? Physicists believed so. But the weak force could not be described by U1 alone. It required a larger symmetry, one capable of capturing its unique behavior. This led to a mathematical structure known as SU2. And so to describe both forces together, physicists proposed a combined symmetry, SU2 x U1. This idea, known as electroweak unification, suggested that electromagnetism and the weak force are 2 aspects of a single deeper interaction. If true, it meant that the early universe, when energy was high and temperature unimaginable, might have possessed a more unified identity. Only later, as the universe cooled, would the forces separate and take on distinct roles. It was an elegant vision, but there was a contradiction embedded within it, one that could not be ignored. A perfect electroweak symmetry required its force carriers, the bosons, to be massless. Yet experiments showed that the weak force was mediated by very heavy particles, the W and Z bosons. Their mass is not subtle. Each is nearly 100 times heavier than a proton. This weight causes the weak force to act only at extremely short range, fading almost instantly. Light, by contrast, is carried by the photon, which has no mass and can travel freely across the universe. How could a unified symmetric force yield such different outcomes? Why would one boson remain massless while the others grew so heavy? If the symmetry was real, something must have happened, something that allowed the mathematics to stay elegant while the universe itself changed appearance. Physicists began to suspect that the symmetry did not disappear. Instead, it was broken. To visualize this, imagine a perfectly round table and a pencil balanced upright at its center. In theory, the situation is symmetric. The pencil could fall in any direction. But once it begins to fall, it must choose a direction. The symmetry remains in principle, yet reality chooses a specific outcome. The universe may have gone through a similar moment. During its early expansion, as the temperature dropped, the electroweak symmetry may have remained mathematically present, but the universe chose a specific orientation that caused the forces to differentiate. In that moment, certain particles acquired mass. Others did not. The symmetry was still part of the equations, but the universe no longer expressed it openly. This concept, spontaneous symmetry breaking, became a turning point in theoretical physics. It offered a pathway to explain why the W and Z bosons were heavy, while the photon remained massless. It suggested that mass was not an intrinsic property of particles, but a consequence of the way the universe settled as it cooled. And yet this raised an even deeper question. What broke the symmetry? What mechanism tilted the balance and selected one outcome among many possible ones? If symmetry once defined the early universe, and if something gently shifted that harmony, then that something must have played a profound role in shaping the universe we inhabit now. This is where the Standard Model, even in its success, showed a subtle incompleteness. It could describe how forces should behave in a symmetric world. It could describe their interactions with astonishing precision, but it could not explain how symmetry broke and why particles had mass at all. A new idea was needed, one not based on the particles we already know, but on a field that had woven itself into the fabric of reality in a quiet, persistent way. A field that permeates all of space, influencing particles without being seen, shifting the configuration of the universe into a state where mass became possible. This idea would arrive from several physicists working independently, among them a soft-spoken theoretical physicist named Peter Higgs. He proposed that a novel field emerged in the early universe, one that filled all space and caused certain particles to interact with it more strongly than others. Through this interaction, particles would gain mass. The symmetry would remain in theory, but the universe would express a specific choice in practice. Before introducing this field in the next chapter, it is worth pausing to appreciate what symmetry reveals about the universe. It shows that reality once possessed a kind of elegant simplicity that has since been concealed. The forces we observe today are like branches from a single trunk shaped by the cooling of the early cosmos. The universe we know may be a product of its broken symmetry, not its original design. And if the universe has already undergone one profound shift, settling into a new configuration as it evolved, then the idea introduced in Chapter 1 no longer feels isolated. The universe may indeed be capable of existing in multiple possible states. The state we live in now may not be unique nor permanent. It may simply be one phase among others. Symmetry gave unity. Its breaking gave structure. What emerged from that breaking set the stage for matter to form stars to ignite and life to find its footing. But the mechanism that allowed all of this to happen, the quiet field beneath reality, remains the key to understanding whether the universe rests at its true minimum or only a temporary one. That mechanism is the Higgs field. And to understand what it is, how it shaped the universe, and why it might not be in its final state, we now follow the idea to the next chapter, where the story of symmetry gives way to the story of mass. By the time physicists understood that symmetry once guided the early universe, a new question emerged with quiet urgency. What caused that symmetry to give way? If the universe began in a perfectly balanced state, something must have shifted to create the world we now recognize, one with mass structure and form. The answer, as unexpected as it was elegant, came in the form of a new kind of field. In the early 1960s, the scientific community found itself facing a puzzle that mathematical beauty alone could not solve. The electroweak theory suggested a unified description of two forces, yet it failed to account for a basic truth of nature: some particles had mass and some did not. Without mass, the universe would have remained a blur of restless light-like particles, unable to settle or bind into atoms. Something had changed the conditions of reality itself. Several physicists were working on this problem simultaneously, each approaching it from their own perspective. Among them was Peter Higgs, a quiet, thoughtful theorist from Scotland. In 1964, he published a short but profound idea, one proposing that the universe is filled with a pervasive field, present everywhere at every moment, even in what we call empty space. This field would later take his name, the Higgs field. To appreciate its significance, it helps to think of space not as a void, but as a medium. According to quantum field theory, every type of particle has an associated field spread across the universe. The electron field, the photon field, the quark fields, they exist continuously, even in absolute darkness. A particle is simply a disturbance, a vibration within its field. The Higgs field fits into this picture, but with one striking difference: it holds a non-zero value, even in its calmest state. This non-zero value is crucial. Most fields rest at zero when nothing excites them, like a still pond at perfect calm. The Higgs field, however, remains gently switched on everywhere, even in silence. Physicists call this its vacuum expectation value, or VEV. It is subtle, uniform, and persistent. But this quiet presence changes the relationship between particles and space in a way that gives rise to mass. One way to understand the Higgs field is to imagine a smooth, invisible ocean filling the universe. Particles travelling through this ocean interact with it in different ways. Some move almost freely, gliding with little resistance. Others interact more strongly, as if pushing through a thicker current. This interaction behaves like inertia, the quality we interpret as mass. The stronger the interaction, the more mass a particle acquires. A particle's mass, then, is not like a hidden weight locked inside it. It is a reflection of how the particle experiences the Higgs field. Mass becomes a relationship, not an ingredient. This view changed physics in a fundamental way. Before the Higgs field was proposed, mass was regarded as an inherent property, an intrinsic attribute. Afterward, mass became a consequence, one dependent on the background condition of reality. If that background changed, mass could change with it. The universe does not merely contain the Higgs field, the universe rests within it. Yet the idea alone was not enough. The question remained: why does the Higgs field have a non-zero value at all? Why did it not settle at zero like other fields? To answer this, physicists examined the shape of the Higgs field's energy. In the early universe, temperatures were unimaginably high, and the Higgs field behaved differently. Its energy curve resembled a smooth, symmetrical hill. At the very top of that hill, the Higgs value was 0 and symmetry remained unbroken. But this balance was precarious, like a pencil standing on its tip. As the universe expanded and cooled, the energy landscape of the Higgs field shifted. The symmetrical hilltop flattened into a new shape, a ring-shaped valley surrounding a central peak. In this new landscape, the center where the field would be 0 was no longer the lowest energy state. The lowest point lay somewhere along the surrounding valley. The universe rolled down into this valley, selecting one point to settle into. In doing so, the symmetry of the original landscape remained in theory, but reality expressed only one of many possible outcomes. This process is known as spontaneous symmetry breaking. The symmetry of the electroweak force did not disappear, it simply ceased to be visible in the structure of the universe. Much like the pencil that falls in one particular direction, the universe chose a specific orientation in the Higgs field's valley. Once that choice was made, particles interacting with the field began to experience mass. In an instant, in cosmic terms, the rules of motion changed. Before this transition, all particles behaved as if massless. Afterward, their motion slowed relative to the speed of light. The photon, however, did not interact with the Higgs field, and so retained its freedom. Light remained massless, able to travel effortlessly across the universe. But the W and Z bosons interacted strongly with the Higgs field, and became heavy, limiting the reach of the weak force to extremely small distances. This one moment of symmetry breaking reshaped the behavior of forces and particles permanently. The idea that a background field could grant mass was revolutionary not only for theoretical physics, but for our understanding of existence. Everything, every atom, every star, every cell relies on this balance. Without the Higgs field assuming a non-zero value, electrons would move too fast to bind to nuclei atoms, would not form, and structure would never emerge. The universe would expand as a radiant mist of energy without substance. It is worth noting that the Higgs field does not give mass to everything. Much of the mass of protons and neutrons, the core of ordinary matter, comes from the dynamic energy of quarks bound by the strong force. The Higgs field provides the mass contribution to the quarks themselves, but the majority of the proton's mass arises from the constant motion and tension of gluons within. Einstein's equation E of mc2 sits quietly behind this, reminding us that mass and energy reflect one another. Even so, the Higgs field acts as the foundation. It establishes the baseline conditions that allow these more complex layers of physics to unfold. Without that baseline, without particles having the correct masses, the strong force would not bind nuclei in a stable configuration. Chemistry would fail to take shape. Life as far as we understand it would not have space to exist. A particularly elegant part of the Higgs mechanism lies in how it treats the electroweak bosons. The symmetry structure of the theory originally predicted 4 massless bosons. After symmetry breaking, these combine and transform, one remains massless, the photon, while 3 become the massive W plus W and Z0 bosons. This merging and separating of fields is subtle, yet essential. It shows how the Higgs field affects not only particles, but also the forces themselves. To picture this, imagine 4 musical notes played as a single harmonious chord. When the Higgs field settles, that chord separates into distinct tones, 1 bright and far-reaching, 3 dense and muted. The music changes, but the original harmony remains embedded beneath it. With the Higgs field incorporated, the standard model became complete in structure. It could now describe how symmetries guide forces, how those symmetries break, and how particles acquire mass. The theory regained its elegance not through removing complexity, but through explaining it. And yet within this completeness, a new question began to surface. The Higgs field rests at a particular non-zero value. This value determines the masses of particles, and therefore the conditions of the universe. But why this value? Why not slightly more or less? If the value were different, the masses of particles would shift. Even a small change could alter the stability of atoms, the behavior of stars, or the possibility of life. This sensitivity hints at something delicate about the Higgs field's resting state. It appears stable. It feels permanent. But the more physicists studied it, the more they wondered whether the universe had settled into the lowest possible state of the Higgs field or merely a stable one among several. This thought, gentle at first, would grow into one of the most profound questions in modern physics. Is the universe resting in the true vacuum of the Higgs field, or in a temporary condition that could in time change again? In the next part of this chapter, we will look more closely at how the Higgs field shapes the structure of reality at a deeper level, and why this resting state may hold a secret about the long-term fate of the universe. To understand why the Higgs field settled into a particular value, it helps to look more closely at how fields behave in terms of energy. Physicists often describe a field's configuration using an energy potential, a kind of landscape showing which states are stable and which are not. A field will naturally settle into the state with the lowest possible energy, just as a ball on a hillside will always roll into the nearest valley. For many fields, this lowest energy state sits at 0. But for the Higgs field, something different occurs. The shape of its potential energy, the curve that describes its preference, resembles a surface with a central high point surrounded by a circular valley. At extremely high temperatures, such as those present in the first fraction of a second after the Big Bang, the top of the central peak was stable enough for the Higgs field to remain there. In this configuration, the universe exhibited electroweak symmetry. All particles were massless, and the laws of nature followed a simpler, more unified form. As the universe cooled, this symmetry could no longer be sustained. The central peak lost its stability, and the surrounding valley became the lowest energy state. The Higgs field rolled off the peak and settled somewhere along the valley. But because the valley formed a continuous ring, every point along it was equivalent in energy. The underlying symmetry remained intact in theory, but the universe expressed only one of these possible states. A single point was chosen, and this selection broke the symmetry in practice. This moment is sometimes compared to water freezing into ice. In liquid water, molecules move freely and symmetrically. When freezing occurs, the molecules lock into a crystalline pattern, choosing specific orientations. The underlying physics remains the same, but the system expresses less symmetry. The Higgs transition was similar, but instead of forming a structure in space, it formed a structure in the rules of physics. One might wonder if the Higgs field has a non-zero value everywhere, what keeps it from drifting or changing over time? The answer lies in the depth of the valley it settled into. The resting point of the Higgs field represents a balance, a state where its energy is minimized. Small fluctuations occur, but the field remains anchored. These fluctuations are what we detect as the Higgs boson, a ripple or quantum excitation of the Higgs field. The Higgs boson is not the field itself, just as a wave on a pond is not the pond. It is a sign that the field exists and that it can vibrate. The discovery of this particle, nearly half a century after Higgs first proposed the idea, became one of the most celebrated achievements in modern science. But the story of that discovery belongs to a later chapter. For now, it is enough to note that the Higgs boson's existence confirmed that the Higgs field is real. It is not a mathematical convenience or a theoretical placeholder. It is a genuine component of the universe, as fundamental as space-time and the quantum fields that govern particles. To see how the Higgs field affects the Standard Model at a deeper level, we need to look at how it interacts with fields rather than particles. Particles are vibrations, but the fields they arise from also interact with each other. In particular, the Higgs field couples to the electroweak fields in such a way that it reshapes their behavior when it acquires its non-zero value. Before symmetry breaking, the electroweak force was mediated by 4 massless fields. Afterward, the Higgs field's settled value caused these fields to mix and transform. This mixing resulted in one field remaining massless, the photon, and 3 combining into the massive W+, W and Z0 bosons. The mathematics behind this transformation is precise, but its consequence can be summarized simply. The Higgs field determined that one force would remain long-ranged while the other would become short-ranged. Light could cross galaxies while the weak force could act only across distances smaller than an atomic nucleus. This separation allowed the universe to behave in the way we now observe. It allowed atoms to hold together through electromagnetic attraction, while permitting the weak force to play a role in processes like nuclear fusion inside stars. Without this differentiation, the universe would express a symmetry too perfect to develop complexity. A natural question arises: was the value of the Higgs field fixed by necessity, or could it have been different? Physics as we understand it suggests that the Higgs field's value is not arbitrary, yet it is not the only value the field could have chosen. If the Higgs field had settled into a slightly different value, the masses of particles would change accordingly. A small shift could alter the stability of atoms, disrupt the balance of forces, or prevent stars from forming. The universe we inhabit appears to be finely tuned for structure. This sensitivity has led physicists to consider whether the Higgs field's value is somehow special. It may be one of many possible outcomes, or it may have been influenced by conditions in the early universe. If the field had settled differently, reality would have unfolded in another form, one in which the familiar building blocks of matter could not assemble. The idea that the Higgs field selected a specific value opens the door to a deeper possibility. The value we observe may not represent the lowest possible state. In many energy landscapes, there are valleys within valleys. A field can become trapped in a local minimum, a stable resting place that is not the absolute lowest energy available. In everyday terms, it is like a ball resting in a small hollow on a hillside. It feels stable, and small disturbances will not move it, yet a deeper valley may exist elsewhere. This brings us to a subtle distinction in physics between a true vacuum and a false vacuum. A true vacuum represents the lowest possible energy state of a field. A false vacuum represents a state that is stable under small disturbances, but not under all circumstances. If the Higgs field rests in a false vacuum, then the universe is stable until it is not. Before drawing any conclusions, it's important to stay within the calm reasoning of physics. A false vacuum does not imply impending change. It simply means the field settled in a state that may not be the deepest. The field may remain there for an extraordinarily long time, perhaps longer than the lifetime of stars or galaxies. Yet the possibility of a deeper state raises a profound question about the long-term nature of reality. To explore this possibility with clarity, we must step from the serene foundations of the Higgs field into the work of physicist Sidney Coleman, who examined the stability of vacuum states in quantum field theory. His insight revealed that the Higgs field may not simply rest, it may wait. Before moving to that question, one final point provides a bridge. The Higgs field did not simply create mass, it created conditions. It allowed the universe to cool into complexity. It turned a landscape of perfect symmetry into one with variety, enabling the laws of physics to express nuance rather than uniformity. The universe we see is the result of that shift. With the Higgs field understood as the agent that tilted reality and gave mass to particles, we're now prepared to explore the more delicate part of the story, whether the value at which it rests is truly final. This brings us to the next chapter, where the calm structure of the Higgs field meets an unexpected insight, one that opens the possibility that the universe may not be resting in the state we imagine it to be. When the Higgs field settled into its non-zero value, it shaped the universe into a state where particles could have mass and structure could form. This transition gave rise to stars' atoms and the delicate balances that allow galaxies to unfold. For a long time, physicists believed this resting value represented the natural conclusion of the Higgs field's evolution, a stable foundation on which the cosmos could build its architecture. But as understanding deepened, a more subtle possibility emerged. What if the Higgs field did not choose the lowest possible resting state? To explore this idea, it helps to understand how physicists describe the ground state of a field. Every quantum field has a configuration that requires the least amount of energy to maintain. This configuration is known as its vacuum state. The word vacuum here does not refer to emptiness, but to the lowest energy arrangement of a field, regardless of whether particles or radiation are present. A vacuum is not the absence of reality, it is the foundation of it. In an ideal physical system, the vacuum represents a true minimum. Like a marble placed in the deepest part of a bowl, the field settles there and remains undisturbed. No small fluctuation or disturbance can move it to a lower point because none exists. A true vacuum is in this sense perfect stability. If the Higgs field were resting in such a state, the universe would be anchored in the most secure configuration available. But nature is often more intricate than the simplest picture. Many systems in physics contain not one but multiple valleys of possible energy states. A field may settle into a state that feels stable, yet lies above another state that is deeper and more favourable. This kind of state is known as a false vacuum, stable enough to persist, yet not the ultimate resting point. A marble can settle in a shallow hollow on a hillside. It will stay there if undisturbed, but a strong enough nudge could cause it to roll into a deeper valley below. This concept applied to the Higgs field leads to a remarkable implication: the universe might not be sitting in the lowest possible energy state. It may be resting in a local minimum rather than a global one, secure for now, but not forever. This idea is known as metastability. At first glance, the possibility of a false vacuum is subtle, almost quiet. It doesn't suggest instability in the ordinary sense. A metastable vacuum can last for an extraordinary length of time, longer than the current age of the universe by many orders of magnitude. If the Higgs field is indeed in a false vacuum, it does not tremble or decay under everyday conditions. It rests with a kind of poised stillness sustained by the energy landscape that surrounds it. One way to visualize this is to imagine a landscape with two valleys. The first is shallow but comfortable with smooth slopes that keep a marble in place. The second, lower valley, lies beyond a ridge deeper, more final. The marble in the first valley can remain there indefinitely unless something provides enough energy to push it over the ridge. From within the shallow valley, life feels stable. Nothing hints at the existence of the deeper valley unless we step back and observe the entire landscape. In the case of the Higgs field, physicists refer to these valleys as minima. The state the Higgs currently occupies may be a local minimum, a false vacuum, while a lower global minimum may exist elsewhere in the Higgs potential. The field rests at a value that is stable under small disturbances but not under all possible influences. The crucial point is not anxiety, but understanding the Higgs field may not yet be at the bottom of everything it could become. If this were true, what would it mean for the universe? It would mean that the universe in its current form is a phase 1 shaped by a particular configuration of the Higgs field, but not guaranteed to be permanent. The laws of physics as we know them arise from the Higgs value we observe. If the field were to transition to a lower minimum, the rules governing particles and forces would change instantly and fundamentally. Masses, charges, and interactions would be rewritten, not adjusted. Matter as we know it would lose its binding structure. This possibility is not stated to provoke fear, but to convey the depth of what physicists discovered reality is tied to the state of a field, and that state may not be absolute. The idea that the universe might rest in a metastable state emerged gradually through careful analysis of the Higgs field's behavior and the shape of its potential energy. The breakthrough came from considering that the Higgs potential might contain a deeper minimum beyond the one it currently occupies. The field may have rolled down into a valley that appeared stable at the time of the early universe, but a more profound valley might have existed beyond it, one the universe never reached. Why would the field fail to reach the lowest valley in the earliest moments after the Big Bang conditions changed rapidly? As symmetry broke and fields acquired structure, some transitions would have depended on quantum fluctuations, tiny shifts influenced by chance. The Higgs field cooling and settling could have chosen a state that was stable enough to support the formation of matter and the evolution of galaxies. But stability alone does not guarantee finality. It is important to recognize that a false vacuum is not wrong or flawed. It is simply not the deepest possible arrangement. The universe could continue in such a state for eons with no sign of change. In fact, from the perspective of everyday experience and everything humans have observed, the universe appears entirely stable. Stars form, galaxies rotate, atoms persist. Nothing hints at the existence of a more fundamental configuration waiting beneath the current one, and yet the concept introduces a subtle, almost poetic idea the universe might be resting rather than arrived. Not unstable, but not at its ultimate destination. To understand why physicists began to take this possibility seriously, one figure becomes central to the story: Sidney Coleman, whose work in the late 1970s illuminated how quantum fields behave when multiple vacuum states exist. Coleman showed that a metastable vacuum is not simply trapped, it is capable of changing through a process that is as gentle as it is profound. Before we turn to his work, one final reflection helps frame what lies ahead. The universe may not be fixed in the most stable configuration, but this is not a source of concern. The timescales involved, if a transition were possible at all, far exceed the lifespan of stars and galaxies. Instead, it provides a deeper appreciation of reality existence as shaped by a choice the Higgs field made long ago, a choice that allowed structure to form. Whether this choice was final or temporary remains one of the quiet mysteries of the cosmos. The next part of this chapter will lead us into the work of Sidney Coleman and the idea of metastability in a quantum universe, an idea that reveals not only how a false vacuum can persist, but how it might one day change. To understand how physicists came to view the Higgs field as potentially metastable, we turn to the work of Sidney Coleman, a theoretical physicist whose insights reshaped how the scientific community thought about vacuum states. Coleman approached the problem not through speculation, but through the quiet, methodical logic of quantum field theory. In the late 1970s, Coleman studied how fields behave when they are not in their lowest possible energy state. His work revealed that a field resting in a false vacuum is not permanently fixed there. Even if it appears stable and remains undisturbed, the rules of quantum mechanics allow for subtle pathways through which the field can transition to a lower state. This process does not require climbing over the energy barrier that separates the two minima. Instead, the transition can occur through a phenomenon known as quantum tunneling. Quantum tunneling is unlike classical motion. In the everyday world, to move from one valley to another separated by a hill, an object must go over the hill gaining enough energy to reach the top before descending. In the quantum world, fields behave differently. They do not need to climb over the barrier. They can, under rare and specific conditions, tunnel through it, appearing on the other side without ever crossing the peak. Coleman applied this principle to vacuum states, showing that a metastable vacuum could in theory transition to a deeper one without being pushed. This insight heightened the importance of understanding whether the Higgs field occupies a true or false vacuum. If the Higgs is in a metastable state, then the universe is not frozen in permanence. It is in a configuration that could, through quantum processes, shift into a more stable arrangement. However, Coleman also made clear that such transitions are extremely unlikely within any ordinary span of cosmic time. The conditions required for tunneling to occur are so rare that even timeframes beyond the lifetime of stars may not be sufficient. Coleman's calculations were rooted in the mathematical behavior of fields, not in imagination or dramatic effect. He showed that quantum fields can fluctuate, and that a fluctuation of the right kind could act like a seed, a starting point from which a new phase could emerge. Just as crystallization in a liquid begins with a single point of structure, a new vacuum state could begin from a tiny region. This region would mark the boundary of a different configuration of the Higgs field, one corresponding to the deeper minimum. To picture this, imagine a still lake freezing on a winter's night. The surface remains liquid until one point cools enough to crystallize. From that point, ice spreads outward, gradually transforming the lake into a solid sheet. In a similar way, a new region of vacuum representing the lower energy state could form in a tiny bubble, and if conditions allow it could expand. What makes this idea remarkable is that the transition would be driven not by external force, but by the internal logic of the field's energy landscape. Coleman demonstrated that if the deeper minimum exists, and if the current vacuum is truly metastable, then quantum mechanics provides the possibility of spontaneous transition. Nothing external needs to trigger it. The field itself contains the potential for change. The universe we observe today would not reveal whether it rests in a true or false vacuum. All observable physics particle masses interactions, forces behave consistently with the value of the Higgs field as it currently stands. Stars burn, matter remains stable, and the cosmic evolution we witness unfolds according to familiar rules. From within a metastable vacuum, reality appears complete. Coleman's work did not suggest that a transition is imminent. In fact, his calculations implied the opposite. If the universe is in a false vacuum, it could remain there for an extraordinarily long time, longer than the predicted lifetime of even the most enduring cosmic structures. The possibility exists not to alarm, but to remind us that the stability of reality is not guaranteed by absolute necessity. It is supported by a configuration that could have been different. The idea that the universe might not be in its final state adds a layer of depth to our understanding of existence. It suggests that the cosmos carries a history of choices made during its early evolution, choices influenced by temperature symmetry breaking and quantum fluctuations. The Higgs field settled into a particular value because of conditions that prevailed when the universe was young. Had those conditions differed, the field might have found a different minimum, and the universe might have expressed entirely different laws. Coleman's perspective showed that stability in quantum field theory is not a binary condition. It exists on a spectrum. A state can be absolutely stable, metastable, or unstable. The Higgs field appears to fall into the middle category, stable enough to support the development of structure, yet not guaranteed to be the final form. One of Coleman's lasting contributions was clarifying that metastability does not produce visible signs. Nothing about the motion of galaxies, the behavior of matter, or the structure of atoms gives away whether the Higgs field is resting in a true or false vacuum. The difference lies in the energy structure beneath the observable laws of physics, subtle, silent, and hidden from direct detection. This idea took time to settle into the scientific community. It required a shift in how physicists thought about vacuum. Instead of a single, absolute ground state, vacuum became a landscape with levels of terrain with multiple basins in which fields might rest. The Higgs field could in principle occupy a state that is stable for longer than the lifetime of the universe, yet still not be the lowest possible energy state. This perspective reshaped how scientists viewed the long-term nature of cosmology. It introduced the possibility that the universe is not static in its most fundamental sense, but may carry the potential for future transformation, even if such transformation lies beyond any scale of time we can meaningfully comprehend. Before moving into the next part of this chapter, it is helpful to bring the idea back to the calm clarity of what we know. If the Higgs field is metastable, it means the universe is stable enough to persist, predictable enough to form structure, and calm enough to give rise to life. The possibility of a lower state does not undermine the reality we experience. It simply adds a layer of depth, a sense that the universe contains more than what is immediately visible. In the next section, we will explore how physicists attempted to evaluate the stability of the Higgs field, not in abstract terms but through measurable quantities. By studying the mass of the Higgs boson and comparing it with the mass of the top quark, scientists gained insight into whether the universe likely rests in a true or false vacuum. These measurements, grounded in experimental data, brought the question of metastability from the realm of theory into the realm of observation. The idea that the Higgs field could be metastable raised a natural question: can we measure the stability of our vacuum? For a long time, this question lived purely in theory. The Higgs field's energy landscape could only be estimated loosely because one crucial value was missing: the mass of the Higgs boson itself. Without knowing that mass physicists could not determine whether the current vacuum was a true minimum or a temporary one, everything changed when the Large Hadron Collider LHC began probing the energy scales necessary to create the Higgs boson. The discovery made in 2012 finally provided the data needed to place the universe on a stability map. But before we reach the details of that measurement in the next chapter, it is helpful to understand why the Higgs mass is so important. The stability of the Higgs vacuum depends on two key numbers: the mass of the Higgs boson and the mass of the top quark. These two values determine the shape of the Higgs potential at very high energies. If the Higgs boson is relatively heavy compared to the top quark, the Higgs potential remains deep and stable. The field would then reside securely in the lowest valley. If the Higgs boson is too light relative to the top quark, the potential may bend downward at extremely high energies, revealing a deeper valley beyond the one the field currently occupies. It is this balance between the Higgs boson and the top quark that forms the core of the metastability question. The reason the top quark plays such a central role lies in its unique interaction with the Higgs field. Of all particles known, the top quark couples to the Higgs field the most strongly. This strong coupling influences the shape of the Higgs potential at high energy scales. In effect, the top quark acts like a weight that pulls on the curves of the energy landscape. If this weight is large enough, it can cause the local valley to slope downward toward a deeper one farther away. Before the Higgs and top quark masses were known with precision, physicists could only run hypothetical scenarios. They estimated that if the Higgs mass fell below a certain threshold, relative to the top quark, the universe would likely be metastable. If it sat above that threshold, the vacuum would be stable, and if it were far below, the universe would have been unstable from the beginning. It would have fallen to a lower state long ago, never allowing matter to form. These three possibilities painted three different stories of the universe. Stable vacuum: the Higgs sits in the deepest valley, the universe is at true rest. Metastable vacuum: the Higgs sits in a shallower valley, stable for now but not the lowest. Unstable vacuum at birth: the Higgs rested on a ridge or shallow point so precarious that the universe would not have lasted a second in its current form. The discovery of the Higgs boson's mass allowed physicists to determine which of these stories best fits our reality. Once the numbers became available, calculations revealed something quietly astonishing. The Higgs sits almost exactly at the boundary between stability and metastability. It is neither deeply secure nor precariously perched. It rests in a state that appears stable, yet mathematically lies just within the region of metastability. The universe, as far as current data suggests, exists in a delicate balance, not at the ultimate minimum, but not dangerously close to transition either. To be clear, metastability on cosmic terms does not imply fragility. The timescales associated with the transition from a false vacuum to a true vacuum are immense. If a transition were possible, the expected lifetime of the current vacuum would exceed the current age of the universe by a factor so large that ordinary language struggles to express it. Stars will burn out, galaxies will drift apart, and black holes will evaporate long before any such change would be likely. And yet the mere possibility carries philosophical weight. It means the universe has a story rather than a fixed certainty. It means the cosmos we inhabit is not defined solely by necessity, but also by the conditions that prevailed during a brief moment in its youth. The Higgs field settled where it did, allowing atoms, stars, and life to form, but it may not be the deepest resting place available. To bring this idea into one final visual analogy, imagine walking along a coastline at low tide. Pools of water collect in natural basins formed by the rock. Each pool feels like its own complete environment, with calm surfaces and self-contained ecosystems. Yet the ocean beyond is deeper. The pool is stable for as long as conditions remain as they are. But it is not the ocean itself. The universe may be similar, a stable yet bounded condition resting within a larger possibility. It is important to stress that metastability, if confirmed, does not diminish the significance of the universe. Rather, it adds layers to its narrative. The universe becomes not a static object, but a phase, a configuration that supports complexity, awareness, and time. The fact that such a configuration arose at all is in itself remarkable. The recognition that we may live in a metastable vacuum leads naturally to the subject of the next chapter, how a transition could occur. If the Higgs field rests in a shallow valley, rather than the deepest one, what mechanism could move it? Classical physics would require the field to receive enough energy to cross the barrier between minima and events so improbable on cosmic scales that it can be effectively ignored. But quantum mechanics offers a different path, one consistent with Coleman's work. Through quantum tunneling, a tiny region of space could in theory shift into the lower state without crossing the barrier. If such a region formed, it could expand, transforming the surrounding vacuum into the true minimum. This scenario is known as vacuum decay. It is a natural process in quantum field theory, though one that would unfold silently and without warning. Before we address vacuum decay directly, it is useful to pause with the conclusion of this chapter. The Higgs field, which gave structure to the universe and made mass possible, may not be settled in the ultimate configuration of reality. It rests with immense stability, yet not with absolute certainty. The universe in this view is a place of extraordinary balance, secure enough to endure, yet resting within a landscape that contains deeper possibility. Whether this balance remains unchanged for the lifetime of existence or merely for a chapter of cosmic history is the question that leads us gently into the next stage of this story. In Chapter 6, we will explore how quantum tunneling provides the mechanism for transition, and what vacuum decay would mean not as a dramatic event but as a natural evolution of the universe's energy state. In the world we see around us, change usually follows a familiar pattern. Something moves only when pushed, heated, cooled, or influenced by a force strong enough to alter its state. A stone remains still on a hillside until wind gravity or a hand sets it in motion. Water stays liquid until the temperature falls below freezing. In everyday experience, transitions require cause and effort. Yet beneath this familiar surface lies a quieter rule of nature, one that belongs to the quantum world. Here change does not always wait for a push. Sometimes it unfolds without crossing the barrier that logic would expect. This phenomenon is known as quantum tunneling, and it reveals a different rhythm of reality, one where the impossible becomes quietly possible. To appreciate quantum tunneling, it helps to imagine a simple scene. Picture a smooth hill separating two valleys. In classical physics, a ball resting in one valley would need enough energy to climb over the hill to reach the other side. Without that energy, it remains where it is indefinitely. The hill is a barrier and the ball cannot cross it on its own. But in the quantum world, this rule softens. Particles behave not only as points but also as waves of possibility that extend beyond their location. These waves do not stop at barriers. They stretch through them, fading gradually, but never dropping to zero instantly. Because of this, there is a small chance that the particle can appear on the other side of a barrier without ever crossing the top. It is as if reality allows a brief, gentle shortcut, one that bypasses the most difficult part of the journey. Quantum tunneling is not speculation or metaphor. It is observed in nature. It allows the sun to shine. In the core of the sun, hydrogen nuclei fuse into helium. Under classical physics, the repulsion between these positively charged nuclei should be too strong for fusion to occur at the temperatures available. But tunneling gives them a chance to merge, releasing the light that warms Earth. The glow of stars rests in part on this quantum shortcut. This same principle applies to quantum fields, the invisible frameworks from which particles and forces arise. Just as a particle can appear across a barrier, a field can change state without being pushed over the energy ridge that separates one configuration from another. This is the heart of how a vacuum state, the resting configuration of a field, might change. When physicists began to consider that the universe might not be in the lowest vacuum state, the next question naturally followed: if a deeper state exists, how could the Higgs field move into it? Classical intuition suggests that the field would require an enormous disturbance, a burst of energy greater than anything the universe currently holds, to climb out of its resting state and fall into a lower one. Quantum tunneling offers a different answer. The field does not need to climb. A tiny region of space could, through tunneling, shift directly into the deeper state. The field would not move gradually or with warning. It would simply be in the new state in a small region first, like a single point on a lake suddenly freezing before the rest of the water follows. This does not happen in a dramatic flash. Quantum tunneling at its core is quiet. It has no sound, no spark, no wave of force. It is a change in configuration, a gentle rearrangement of the underlying structure of reality. To understand how such a change begins, imagine the landscape of the Higgs field as a map. The current state is a valley, comfortable and seemingly stable. If a deeper valley exists, a ridge separates the two. For the field to move, it must find a passage through that ridge, and tunneling is the only known mechanism by which this could occur spontaneously. A single seed region, microscopic in scale, could form in the lower valley. If that seed is large enough, the new state would sustain itself and begin to expand. If not, the seed would vanish as quietly as it appeared. The remarkable thing is that this possibility, while allowed by quantum mechanics, does not disrupt the calmness of the cosmos. It operates on timescales that stretch beyond comprehension. The mathematics describing these transitions suggest probabilities so small that even the entire lifespan of the universe may not be long enough for such an event to occur. The universe carries the possibility, but not the urgency. Quantum tunneling also resists intuition because it does not follow cause and effect in the way we are accustomed to. It does not require a trigger, no collision, no cosmic event, no imbalance. It arises from the fundamental uncertainty embedded in quantum systems. Fields are never perfectly still. Even in their quietest state, they fluctuate. These fluctuations are usually too small to do more than stir the field gently. But in theory, one fluctuation given enough time could be just the right shape to begin a transition. It is here that the quantum nature of reality offers a kind of calm perspective. The universe does not need to be pushed into change. It has the capacity to shift only if the conditions allow it. And those conditions, based on present understanding, make such a shift unimaginably rare. The field rests. It has rested for billions of years. And if the mathematics holds, it may continue to rest for a span far beyond the lifetime of stars. Quantum tunneling does not imply instability in the ordinary sense. Instead, it illuminates a more nuanced idea that the universe contains possibilities that remain mostly dormant. The Higgs field. If metastable holds within it the potential to choose a different configuration, but the likelihood of such a choice is so remote that it becomes more a conceptual insight than a concern. As we explore the implications of tunneling, it is helpful to approach the topic with the same quiet tone that nature seems to follow. Nothing in the universe shows any sign of such a transition. Galaxies rotate, atoms remain bound, and the night sky unfolds with familiar constellations. The idea of a vacuum transition, though scientifically valid, rests not in the realm of everyday experience, but in the deep background of theoretical physics, a whisper rather than a warning. Before we move to the next part of this chapter, one thought can sit gently in mind. The universe is not static by necessity, but by grace of the conditions it inhabits. Quantum tunneling is a reminder that the cosmos is both structured and subtle. It holds room for change, yet offers stability vast enough to span ages. We will explore what would happen if such a tunneling event were to occur not in dramatic terms, but through the natural quiet evolution of a new vacuum state forming in a tiny region of space, and how it would unfold. If a quantum tunneling event were to occur within the Higgs field, it would not unfold with sound brightness or any sensation we associate with change. It would begin in silence on a scale far smaller than any atom. A tiny region of space so small that no instrument today could detect it would shift into the lower energy vacuum state. This region is often described as a bubble of true vacuum. The word bubble here is not literal, but it provides a helpful way to imagine the structure. A bubble marks a boundary. Inside lies a new state. Outside remains the old. The boundary known as a bubble wall is the interface where the field transitions from one configuration to the other. On one side, the Higgs field holds the value that defines the universe as we know it. On the other side, it rests in a different value, one that belongs to a deeper energy minimum. At first, such a bubble would be fleeting. Most bubbles, if they ever form, would be too small to sustain themselves. They would collapse back into the existing vacuum almost instantly, leaving no trace. Only a bubble that exceeds a certain critical size could continue to grow. If this threshold were crossed, the bubble would no longer shrink. Instead, it would expand, pushed outward by the energy difference between the two vacuum states. In classical physics, expansion suggests force and outward push, driven by pressure or motion. Here the concept is gentler. The expansion of a true vacuum bubble is a natural consequence of the field seeking the lowest possible energy state. Once a region of the lower vacuum is large enough to be energetically favoured, the universe allows the transition to continue quietly and without friction. Inside the bubble, the rules of physics would be different. The Higgs field would hold a new value, reshaping the fundamental interactions that govern particles. The forces that bind matter the masses of particles, and the behaviour of atoms would no longer resemble the conditions we are familiar with. This does not imply destruction or violence within the bubble. It means that the physical framework inside would not support the structures that exist outside. Matter as we know it would simply not form in the same way. The boundary of the bubble, meanwhile, marks a region of transformation. As the bubble expands, it converts the surrounding vacuum from the current state to the lower one. This process is not like a wave or an explosion. It is a shift in the underlying field, replacing one configuration with another. The bubble wall can be thought of as the leading edge of a new chapter of physical law. One of the most striking features of this scenario is the speed. Calculations show that if a true vacuum bubble were to form, it would expand outward at nearly the speed of light. Nothing can outrun or escape it, because information itself cannot travel faster than the speed at which the bubble spreads. This sounds dramatic in abstract terms, yet in a serene context it reflects a quiet truth. If such a transition were ever to occur, it would be instantaneous from any observer's perspective. No one would see the bubble coming. There would be no warning, because the bubble wall would reach any point at the same moment its presence became knowable. The transformation would be seamless, without time for reaction or reflection. But it is important to remember that this description belongs to the abstract realm of quantum field theory. In lived reality, the universe shows no sign of such a transition approaching, and the estimated probabilities make it a remote possibility, not an imminent concern. Understanding the expansion of a true vacuum bubble provides insight into the nature of cosmic stability. The universe is not like a fragile structure waiting to fracture. It is more like a landscape that contains paths it could take, though time itself may not be long enough for those paths to ever be walked. The bubble scenario describes what could occur under the rules of quantum mechanics, not what is expected to occur under the conditions of our universe. Inside the bubble, the new vacuum would carry its own definition of normal. If particles could form there, they would be shaped by laws unlike those we know. The forces that hold matter together might differ in strength. The building blocks of atoms might not assemble into recognizable structures. Space and time themselves might curve in unfamiliar ways. This is not a picture of loss, but one of difference. A new vacuum state would be a new physical reality, consistent within itself yet separate from ours. The expansion of the bubble continues until all regions of the previous vacuum have been replaced, or until the bubble meets another bubble if more than one were to form independently. In theory, bubbles originating from different points would grow and eventually merge. Their interiors, being expressions of the same lower vacuum, would align. The universe would settle into a final equilibrium, resting at the lowest possible energy state. This transition, if it ever occurred, would not leave remnants of the old vacuum. The shift is complete because the field does not transform gradually, it reconfigures entirely. Just as ice replaces liquid water fully, the new vacuum would replace the old with clarity. Yet unlike water turning to ice, this change would not be governed by temperature or time, it would be guided only by the geometry of the field's potential. While this picture may sound absolute, it sits at a great distance from human timescales. The stability of the current vacuum has held for billions of years. Galaxies have formed, stars have lived and died, and life has emerged and reflected on its own existence, all within the calm that the present vacuum provides. The bubble scenario does not lessen the beauty or meaning of this stability. It simply reveals that the universe at its most fundamental level is dynamic in possibility, even if still in experience. Before we continue to the final part of this chapter, it is worth holding one gentle perspective. The universe as we know it is complete in itself. Its laws have allowed structure, time, and awareness to appear. The existence of a deeper vacuum state does not diminish this chapter of reality. It only suggests that the cosmos contains more layers than we currently inhabit. We will reflect on why, despite this theoretical possibility, scientists remain calm. We will explore why the universe is considered safe on unimaginably long timescales, and how this understanding invites not fear, but appreciation of the rare balance that allows us to witness the cosmos at all. The possibility of vacuum decay often appears dramatic when first encountered. It has been described in scientific literature with words that evoke finality, transition, decay, end of known physics. Yet when viewed through the lens of scale probability and the quiet rhythm of cosmic time, a different feeling emerges, one that aligns more closely with the serenity of the universe itself. For all the elegance of the bubble scenario, nature gives no indication that such a transition is likely to occur. The estimated lifetime of a metastable vacuum surpasses the age of the universe by magnitudes so vast that numbers struggle to convey the distance. If the universe has existed for roughly 13.8 billion years, the predicted timescales for a vacuum transition extend far beyond even the lifespan of black holes, which themselves evaporate over extraordinary stretches of time. In this context, the current vacuum feels less like a temporary phase and more like a long, peaceful chapter, one generous enough to allow galaxies, stars, planets, and life to unfold. It helps to hold this perspective gently. The universe has already persisted through cosmic epochs, stellar cycles, and transformations of unimaginable scale. If the current vacuum were fragile or poised on the edge of transition, we would expect instability to have revealed itself long before now. Instead, the universe has remained calm and coherent. It suggests that whatever the deeper structure of the Higgs field may be, the present configuration is steady enough to sustain existence for longer than any familiar measure of time. Another reason for this calm confidence is that the stability of the vacuum is not influenced by external events. No cosmic collision, no supernova, no black hole, and no human technology can meaningfully trigger a vacuum transition. The scale of energy required to alter the Higgs field across the ridge between minima is so far beyond reach that even the most energetic processes in the universe fall short. This means that vacuum decay is not something that can be provoked or accelerated. It is governed only by the subtle rules of quantum mechanics, and those rules suggest stillness, not urgency. In this sense, the universe is not fragile. It is deeply insulated from abrupt change. Even if a quantum tunneling event were possible, it would be independent of external influence. It cannot be caused in any familiar sense. It is a quiet mathematical possibility, not a threat. There is also a philosophical gentleness in understanding vacuum decay. If it were ever to occur, it would not be an event witnessed or felt. Since the bubble wall would travel at nearly the speed of light, there would be no moment of anticipation or awareness. No suffering, no alarm, no sense of loss. The transition by its nature would be seamless. This removes the emotional charge that the concept sometimes carries. The universe offers no narrative of fear here, only the neutrality of physics. When scientists discuss vacuum decay, they do not do so with anxiety. Instead, they treat it as a fascinating consequence of quantum field theory, an elegant implication of how fields behave when multiple energy states exist. It is a topic that inspires curiosity rather than concern, inviting reflection on the delicate balance that makes the universe possible. This quiet perspective opens a door to a more contemplative appreciation of existence. The fact that the universe may not rest in the absolute lowest energy state can be seen not as a flaw, but as a reminder of how remarkable it is that such a state, metastable or not, has given space for complexity to emerge. Atoms formed stars, ignited chemistry, unfolded, and life found a foothold. Consciousness became possible. The current vacuum, whatever its deeper status, has supported everything we know. The idea of a metastable universe can even be comforting in its own way. It suggests that reality is not rigid or fixed, but part of a dynamic and vast landscape, one that extends beyond our chapter of physics. Just as earlier eras of the universe experienced different conditions, future eras may hold states of existence we cannot envision. This perspective encourages humility, not fear. We are living within one expression of what the universe can be. It also invites a quiet wonder that the cosmos is capable of change on scales so immense that they lie outside the reach of stars and galaxies. The vacuum is not merely empty space, it is the canvas on which physics paints its laws. To imagine that the canvas itself could shift is to glimpse the depth beneath the surface of existence. It expands the sense of what reality is without asking us to worry about what comes next. For those who take comfort in stability, the scientific view remains reassuring. If metastability is correct, the universe has enough time ahead to see the birth and death of countless generations of stars long after ours fade. If stability is the true answer, then the vacuum will never change at all. Both outcomes offer calm. In either case, the present moment of the universe is secure on scales far beyond our own lives, our species, or even our planetary history. This understanding leads to a gentle reflection. The universe is not a place on the verge of collapse. It is a place of extraordinary patience. Whether the current vacuum represents a long chapter or an eternal state, it is spacious enough to embrace billions of years of cosmic evolution. And within that span we find our brief moment one where we can observe, learn, and appreciate the cosmos that shelters us. As we leave this chapter, it may be soothing to carry one simple thought: the universe is calm. It unfolds according to laws that allow harmony and continuity. The concept of vacuum decay, far from being a source of fear, is an example of how deeply physics seeks understanding. It reveals that reality holds more layers than what we see, yet remains gentle enough to sustain all that we know for longer than language can describe. In the next chapter, we will step from the quiet possibility of change to the question of measurement. We will explore how the discovery of the Higgs boson allowed physicists to place the universe on the stability chart, and how the masses of the Higgs and top quark reveal where our vacuum lies in the cosmic landscape. For decades, the question of whether the universe rests in a stable or temporary state remained suspended in theory, elegant, compelling, yet unconfirmed. Physicists could draw the energy landscape of the Higgs field on paper, propose equations and outline possible outcomes for the fate of the cosmos, but one essential piece was always missing: a number, a single value that would anchor speculation into reality. That number was the mass of the Higgs boson. The search for the Higgs was not a race driven by urgency, but a quiet pursuit of clarity. It stretched across generations of physicists. Some of those who helped build the theoretical framework in the 1960s and 1970s would not live long enough to see the particle confirmed. Their work rested like a seed carried forward by new hands, new minds, and new technologies that would eventually test the mathematics born decades earlier. Before its discovery, the Higgs boson existed as a prediction, a missing piece of a puzzle whose presence could be felt only through the consistency of the equations that required it. The standard model of particle physics worked beautifully in describing the interactions of known particles and forces, yet there was a quiet incompleteness at its core. It was as if a story had been written without the final chapter. Everyone trusted that the chapter existed, but no one had seen the words on the page. To detect the Higgs, scientists needed to recreate conditions resembling the earliest instance of the universe, moments of extreme energy and density that no natural environment on Earth could provide. This meant building a machine capable of accelerating particles to extraordinary speeds and letting them collide with enough force to momentarily reveal the physics of creation. This aspiration eventually took shape beneath the border of France and Switzerland in a circular tunnel 27 kilometers long. There, the Large Hadron Collider, or LHC, would send streams of protons hurtling toward each other, guided by powerful magnets and timed with exquisite precision. When they collided, they produced sprays of particles brief and countless, each revealing a trace of the underlying laws of nature. For many years, the Higgs boson remained hidden within the data. Each collision produced patterns that needed to be sorted, filtered, and examined. Only a tiny fraction held the signatures that scientists were searching for. The process required patience, an almost meditative kind of patience, because the universe does not reveal its most subtle truths quickly. The data grew night after night, stored in vast archives, waiting for someone to find the unmistakable signal. Then in 2012, something changed. Two independent experiments at the LHC Atlas and CMS began to see a consistent pattern emerging from the background noise. A particular decay signature appeared more often than chance should allow. It hinted at the existence of a particle long theorized but never seen. As the months passed and the analyses deepened, confidence grew. The signal strengthened. When the result finally reached the statistical threshold required for scientific discovery, the physics community gathered to share the moment. On July 4, 2012, the announcement was made. A new particle had been detected and its mass measured to be approximately 125 billion electron volts. It matched the expected properties of the Higgs boson. The final chapter of a story that began in the minds of theorists had been written into the record of experimental science. There was a quiet beauty in that moment. The discovery did not change the way planets move or how sunlight warms the Earth. Life continued unchanged in its rhythm, but the foundation beneath understanding had shifted. With the Higgs mass now known, the question that had waited patiently for decades could finally be approached with clarity. Was the universe resting in a stable vacuum, or was it balanced gently in a metastable one? The discovery did not answer that question directly. Instead, it provided the key that would unlock the next step. The Higgs mass alone was not enough. Another number was needed to complete the picture. That number belonged to a very different particle, the top quark. It is the heaviest known fundamental particle, and its mass influences the shape of the Higgs potential at high energies. The top quark's value would determine whether the Higgs rests in a valley that is deep enough to be final or shallow enough to be temporary. Meanwhile, as physicists compared these numbers, a calm realization settled in. After decades of waiting for the Higgs, the universe did not rush the moment. It had been patient from the beginning, allowing humanity the time to learn to build to ask. The discovery itself was not loud or urgent. It arrived like a gentle confirmation that the theories built over half a century were not just imagination. They traced the structure of reality. Looking back, the decades of searching for the Higgs can be seen as a mirror of the universe's own pace. Nothing in the cosmos demands speed. Stars form over millions of years, galaxies drift over billions, and particles that shape existence wait quietly to be found. The pursuit of the Higgs was not a chase but a long and contemplative journey toward understanding. The importance of the Higgs discovery for vacuum stability lies not in the particle's existence, but in its measured mass. With this value in hand, physicists could begin to place the universe on a conceptual map, a chart showing where our vacuum sits in relation to stability, metastability, and instability. It is a map not of locations but of possibilities, not of stars but of states of reality. Before we explore that map in the next section, it may be helpful to pause with a simple thought. The discovery of the Higgs was not merely a scientific achievement. It was a moment that connected generations of inquiry, those who imagined it, those who sought it, and those who finally saw it. It marked the transition from prediction to presence, from theory to observation. In the gentle quiet of that realization, one truth becomes clear: the universe does not reveal itself all at once. It opens slowly, as if guiding us through its mystery with the same patience that shaped the stars. And now that the Higgs has been found, the next step is to understand what its value tells us about the nature of our cosmic home. We will explore the numbers themselves, how the masses of the Higgs and top quark create the map of vacuum stability, and what those numbers reveal about where our universe resides within that landscape. With the Higgs boson finally discovered and its mass measured, the abstract question of vacuum stability could begin to take a more defined form. The next step was to understand what this number meant for the structure of the universe. A single measurement by itself is like a star without coordinates, beautiful but not yet placed in the sky. To know its role, the Higgs mass had to be compared with another value that exerts a subtle but profound influence on the Higgs field, the mass of the top quark. The top quark may seem like an unlikely partner in this cosmic inquiry. It is not a particle most people hear about often, nor does it influence daily experience in any direct way. Yet among all known particles, the top quark holds a unique distinction. It interacts with the Higgs field more strongly than any other. In a sense, the top quark presses on the Higgs potential, with greater weight shaping the curvature of the energy landscape at extremely high energy scales. This influence determines whether the valley where the Higgs rests slopes gently toward a deeper one beyond. To understand why it helps to picture the Higgs field not as a static backdrop but as a living part of the universe, one that responds to the presence of particles. When the Higgs interacts with particles, it gives them mass. But the strength of that interaction varies, and the top quark couples to the Higgs more intensely than any of its companions. This strong coupling subtly affects the shape of the Higgs potential as energy increases. If the top quark is heavy enough, it can cause the potential to bend downward at high energies, hinting at a deeper state beyond the one the universe currently occupies. This interplay between the Higgs mass that defines the height of the valley and the top quark mass that influences its slope creates a delicate balance. It is this balance that physicists sought to measure. The mass of the Higgs boson had been identified near 125 GeV, but to interpret its meaning, the mass of the top quark also needed to be known with high precision. The top quark, though discovered in the 1990s, carries a mass that is far less straightforward to pin down. It decays rapidly, appearing only briefly in particle collisions before transforming into lighter particles. Detecting its mass requires careful reconstruction of its decay patterns, an exercise in both experimentation and interpretation. Over the years, through experiments at facilities including Fermilab's Tevatron, and later the LHC physicists refined their measurements. The top quark's mass settled near a value of approximately 173 GeV. These two numbers, 125 and 173, may seem abstract, but together they act like coordinates on a chart. One marks the height of the current vacuum, The other marks the weight tugging on its shape at high energies. With them, the universe could finally be plotted on the vacuum stability map. This map divides the possible combinations of Higgs and top quark masses into 3 broad regions. A region where the Higgs mass is high enough relative to the top quark that the vacuum is stable. A region where the Higgs mass is too low, causing the vacuum to be unstable, unable to survive the early moments after the Big Bang. And a region between them, an intermediate zone where the vacuum is metastable. Not the deepest state, but deep enough to persist for extraordinarily long durations. With the Higgs mass measured around 125 GeV and the top quark mass near 173 GeV, the point representing our universe falls gently in the metastable region, slightly to the side of perfect stability, yet far from instability. It is as though the universe rests on a plateau steady, wide and calm, even if not the absolute lowest point. This result surprised many physicists. Some expected the vacuum to be stable, concluding the story with finality. Others thought it might be unstable, requiring new physics to explain how the universe survived. Instead, nature chose the narrow path in between where the universe appears stable for all practical cosmic purposes, yet mathematically not at the lowest possible energy state. The numbers aligned almost precisely along the boundary, as though the universe exists in a place of balance rather than certainty. Still, these values carry uncertainties. The mass of the top quark in particular remains one of the most challenging measurements in particle physics. Tiny shifts in its value, even fractions of a GeV, could move the universe's location on the stability map slightly higher or lower. Physicists continue to refine the measurement, not driven by worry but by curiosity. The closer the numbers are pinned down, the more precisely we understand the nature of our cosmic home. Yet even with these uncertainties, the broad conclusion remains unchanged: the universe rests comfortably. Whether the vacuum is absolutely stable or gently metastable, it is secure over timeframes so immense that they defy ordinary comprehension. These numbers do not place an expiration date on reality. Instead, they provide a deeper context showing that the cosmos sits within a landscape, rich with structure shaped by 2 values that were once unknown. There is a quiet beauty in the way these numbers guide understanding. They are not simply data points. They are the coordinates of existence itself, locating our universe within the vast possibility of how physics could have unfolded. If the Higgs had been slightly lighter, the story would have been different. If the top quark had been slightly heavier, the early universe might never have settled into a form capable of supporting stars and life. The map of stability reveals just how delicately the conditions align. Before moving on to the final part of this chapter, it may be comforting to reflect on how this information fits into the larger picture. Rather than diminishing the universe, these measurements enhance the sense of wonder. They show that existence is not accidental but balanced with remarkable precision. The numbers do not suggest fragility, but harmony and arrangement that has sustained billions of years of cosmic evolution, and by all current understanding will continue to do so for far longer. We will gently place these numbers on the stability map and explore where the universe sits within this landscape, not as a warning but as a perspective that deepens the appreciation of the calm, enduring nature of reality. With the masses of the Higgs boson and the top quark now measured, a quiet clarity emerged. At last, physicists could place our universe on the vacuum stability map, a conceptual chart that marks where different combinations of values would lead. It is not a map of stars or galaxies, but one of possibilities showing how the fabric of reality itself could be configured. To imagine this map, picture a gentle graph with shaded regions. Along one axis lies the mass of the Higgs, along the other the mass of the top quark. Each point represents a different version of physical law, a different universe in a sense, with its own storyline defined by how the Higgs field settles. Some regions on the map correspond to universes that could never form structure. Others correspond to universes that would sit in perfect stability forever, and between them lies a narrow band where the universe remains calm yet not in the deepest possible state. This is the region labelled metastable. There is comfort in knowing that we live in a chapter of the cosmos that is complete enough for stars to shine, for worlds to form, and for minds to look upward and ask questions like the ones we explored together. We do not need to reach the end of the story to find meaning in the part we are living. This moment, this universe is enough. As the night sky returns to its quiet rhythm above us, you might carry a softer sense of perspective with you, the sense that reality is vast, layered and unfolding at a pace far beyond the measure of our days. And within that immensity, there is room for calm, for gratitude, and for rest. Let the thoughts settle now like dust drifting gently through a beam of starlight. The universe holds its balance, the laws that cradle us remain steady, and everything that matters continues quietly in its own time. This is a good place to pause, a good place to breathe, a good place to rest, knowing that the cosmos is still and you are safe within it.